Chapter 5 deals with the elasticity equations. Those are the equations for displacements and stresses and strains in a elastic body, for example, a metal under in the presence of boundary or body forces. And in Chapter 3 we derive the diffusion equation by looking at a small piece of the region and calculating how much material was entering through the boundary and how much was being created, and setting that equal to the rate of change of material in the body. Well, we're going to do something similar here, except instead of dealing with the amount of a diffusing substance, we're going to deal with the forces. And the key is that if we look at a small piece of this elastic body, we got a big metal block or something, we're just looking at an arbitrary small chunk of it, S, and then we use Newton's second law to say that the density times the acceleration vector. Okay, so UVW is the displacement vector. That means that's how much the body at the point XYZ is displaced at a given time. So UVW is the displacement vector, and the acceleration then would be U sub tt comma V sub tt comma W sub tt, and you multiply that by the mass per volume, and that will give you the the mass times acceleration. And on the right hand side we want to have the three components of the forces. Well, there can be an external force, vector F1, F2, F3 could be the force per unit volume due to gravity or some external force. But we also have a force on that portion S of the body that's exerted by the rest of the body, and that's what this thing tells you here, that the force vector on a portion of the boundary of S that has normal vector nx, ny, nz, that's a unit normal to the boundary. A piece of boundary of S with that unit normal will experience this force acting on it, where this is called a stress tensor or matrix. In other words, the x component of the force of the rest of the material acting on that portion of the boundary would be sigma xx nx plus sigma xy ny plus sigma xz times nz. And you can think of sigma pq as being the force in the p direction, p being x, y, or z, exerted by the rest of the boundary per unit area on a piece of boundary whose unit normal is in the q direction. Well, may have lost you on that, but anyway, this stress tensor is a matrix such that if you multiply that matrix times the outward unit normal, that will give you the force on the boundary of the rest of the material. So you integrate that over the boundary. There's your three components of the boundary force integrated over the boundary, and that these three components will give you the net force of the rest of the material on the little piece S. Okay, well, then we use the divergence theorem. So this is the dot product of the first row of this matrix with the unit normal over the boundary. Then that's going to be equal to the divergence of that first row integrated over the whole region S. So we get the left-hand side are the three components of mass per unit volume times acceleration. Right-hand side are the forces per unit volume. These are due to the rest of the material. That's the force the rest of the material exerts on S, and this is the external force due to gravity or whatever. So similarly to chapter 3, then we say, well, those are equal for integral over arbitrary s, so take s to be so small that both sides are essentially constant, and you can say that that integrand must be equal to that must be equal to that, and so forth. So there's your equations for elasticity. The sigma xx, that doesn't denote derivatives, by the way. Maybe I should have called that sigma 1, but that does denote a derivative. And this is a second time derivative. Now, how do these stresses, though, relate to the displacements? Well, they are related by the following formulas, which we aren't going to derive, but it's known that the stresses are related to the displacements by these equations here, where E is the elastic modulus, Young's modulus, and nu is the Poisson ratio. And so we're just going to take these equations on faith, or if we solve these for the stresses in terms of the displacements, derivatives of the displacements, we get the next page. We get these equations. So basically you can plug this in for sigma xx. Remember that xx is not derivatives, that's just part of the notation. So sigma xx is that, sigma yy, and so forth. Plug these into those equations I just showed you. And remember, we have first derivatives of the stresses, and the stresses are functions of the first derivatives of the displacements. So you get second derivatives of the displacements in that equation. So once you plug these formulas in to the basic equation, here you actually have 3 second order equations involving derivatives of u, v, and w. Derivative with respect to time here, and derivative with respect to x and y here, and z. Now, the steady state equations, you just replace the left-hand side by 0. In other words, if you run an elastic body out in time until things quit changing, until it reaches an equilibrium, then these will be 0, and that's called those are the steady state elasticity equations. And boundary conditions usually will have either u, v, and w are given. If you know the displacements on a piece of the boundary, that would be, in Galerkin terminology, the fixed boundary conditions. And if you know the force, if like there's an external boundary force, and remember F1, F2, F3 is a body force, that's a force interior to the region per unit volume. This is a boundary force per unit area on the boundary, vector G1, G2, G3. And since, remember, this matrix times the outward unit normal gives you the force on the boundary, then you set that equal to the external force. That's like the internal force balanced with the external force. So there's your typical force boundary conditions. If as in our example, if there's no boundary forces, if it's free, then basically G1, G2, G3 will be 0. And this is actually going to be very natural boundary condition for the Galerkin method. We're going to first do a two-dimensional example, and in a thick two-dimensional plate, we can assume that there are no strains in the z direction. So W will be 0 everywhere, and their U and V are constant in the z direction, so U sub z and V sub z are 0. So these disappear, the W's disappear, and you get sigma xx is equal to that without the W, sigma yy is that without the W, sigma xy, which is the same as sigma yx, is that. So reduces to, the plane strain equations reduce to the following two-dimensional problem. Okay, so for a two-dimensional body, you only have displacements in the u and v, the x and y direction, and W is assumed to be 0. And there's your equations in 2 dimensions where sigma xx is, the W sub z term is gone. There's sigma yy, and there's sigma xy, and it's the same as sigma yx. So we're going to solve these plane strain two-dimensional equations, steady state, so left-hand side the time derivatives are 0. We're going to solve them in a little arch, St. Louis arch. So our two-dimensional plate will look like this, and there's going to be a body force due to gravity of -10, so that's the downward force of gravity of, so the external force is 0, -10, the force per unit volume or per unit area for 2D problem. So F is the vector 0, -10, and the boundary conditions are here where the arch touches the ground, U and V are going to be 0. It's glued to the ground there. The top and the bottom surfaces are going to be free surfaces, that is 0 boundary forces. So 0 displacements here and here, 0 boundary forces here and here. And we'll take the elastic modulus to be 100, the Poisson ratio to be 0.2. Poisson ratio is always between 0 and 1/2. And the boundary force per unit area is 0 -10. The body force, there is no boundary force, it's on the top or bottom. The dimensions of the region are, this is r equals 6, that's r equals to 10. Okay, so we're going to solve it using Galerkin method, and it will be surprisingly natural. The Galerkin method actually handles these kind of problems much more naturally than collocation. So here we go. Don't want to do a prepared example. Two-dimensional problem. Have to use Galerkin method. We're going to use Galerkin method anyway. Double precision, yes. Okay, parameters. We want the elastic modulus to be 100. We want the Poisson ratio, which I'm going to call V and U. Nu equals 0.2. And I guess those are the only parameters we have here. Now we have to define initial triangulation for a Galerkin method problem. If the region is rectangular, which this isn't, it's real easy to automatically generate the initial triangulation. If it's general, it's complicated. We have to actually define the vertices and coordinates of the vertices in the initial triangulation. But this is, if it's a simple region, basically if it's one that can be described by x and y functions of p and q, and this is because it's an part of an annulus, so we can easily define x and y to be p cosine of q and p sine of q. P is basically r and q is theta, and theta will go from 0 to pi because it's half of a circle, and p, which is r, will go from 6 to 10. So if you can define your region that way, in other words, if it's simple enough that we could have used collocation method as far as the region is concerned, then PD2D will make it easy for you. And so that's the option we want. And we have to define x and y as functions of p and q. It's kind of like the P1 and P2, except we won't actually use P and Q in the equations or boundary conditions or anything. This is just strictly for the initial triangulation, whereas with the collocation method, the P1 and P2 are used throughout the definition of the problem. Okay, so we just use polar coordinates, and in P grid, P being R, basically, let's see, let's do about 6 grid lines in the R direction. We want to go from 6 to 10. Remember, R goes from 6 to 10. And theta, which is Q, is going to go from 0 to pi. So I'll leave 21 in that direction. We'll see what the initial triangulation looks like in a minute. So theta goes from 0 to pi. R, which is P, goes from 6 to 10. Now the arc numbers, remember a negative arc number for Galerkin, the boundary conditions are very different format for collocation and Galerkin. You have to keep these straight. For Galerkin, you need a negative arc number if you have fixed boundary conditions. That means all your displacements, all your unknowns are known. And the unknowns are going to be u, v, and w, the displacement components. And so where they are given, namely when q is 0 or pi, the u and v are going to be 0. So those will be negative boundary arc numbers. But IP arc of 1, that means the P equals 6, R equals 6. We need to give positive boundary number there because that's going to be free boundary. That's going to be the boundary forces are given, namely they're going to be 0. And so give positive numbers for the top and the bottom, and I need to give negative numbers for the two ends, the two flat ends where the region touches the ground. Final triangulation, well, we have 400 triangles in our initial triangulation, all generated automatically, thank goodness. So final triangulation, let's go up to 1,000. And let's use a uniform triangulation, so don't worry about this stuff. It recommends the solver 4 unless you have reason to use another one. I'll use degree 2 elements. Steady state. Is it linear? Yes. Elasticity problem linear. Okay, we've got two differential equations and two unknowns because this is 2D elasticity problem. So two equations, I'm going to call them u and v, the unknowns u and v. For the 3D problem, we'll have three equations involving u, v, and w. Is this symmetric? Well, actually it is, but I don't want to explain that, so let's just say no. And do I want a boundary, an integral? And I do, just so I can compare the result, because I happen to know what the integral of v over the whole region is going to be. It's given in the book, so that'll give me something to check it by. Don't want any boundary integrals. Don't have any Dirac delta. Okay, now the boundary conditions. Well, basically it's going to be the derivative with respect to x of sigma xx plus derivative with respect to y of sigma xy equals F1, which is 0. The external forces are 0 and minus 10. Actually be plus 10 because remember that the equation was rho uxx equals this minus F2. So so F2 will actually be 10, because if you take it on the other side, it'll be minus 10, which is what we want. Now, sigma xx and sigma xy and sigma yy are defined in terms of ux and vy and so forth. And I'm going to read those equations from a file here. So here's where I should type in definitions for sxx and sxy and so forth in terms of, well, this is what I should type in, but I didn't want to, so I put it in a file called pd2d.in, and I input a pound sign. It starts reading from that file until it gets another pound sign, which it did here. So that basically just saves me the trouble of typing all that in and wasting your time. Now, F1, as we said, is 0. A1 is just sxx. Remember, the equation is derivative with respect to s of sigma xx plus derivative with respect to y of sigma xy equals F1, so forth. And so A11 is just sxx. B1 is sxy. F2, it was 10. And A2 is syx, which is the same as sxy. I'll put that in again. And syy is B2, and that takes care of the partial differential equations. It's very simple for the Galerkin method, simpler than it is for collocation. Now, fixed boundary, well, we do have two fixed boundary arcs, but you only need to input them if the defaults won't do, and the defaults are that all variables are set equal to 0 on the boundary. So if they're set equal to 0 as they are at the two flat ends of this arch, you don't even need to input those. So we'll say no, we don't have any. We do have two negative arcs, but the defaults will work there. Now the free boundary conditions, well, the defaults also work there because the defaults are boundary forces equal to 0. So, well, let's input one of them anyway. So let's say, yes, we do have an arc number 1 where the boundary conditions are that, but that GB1, GB2 are just the two components of the boundary force, because this, remember, this is sigma xx. Sigma xx times nx plus sigma xy times ny equals GB1. Well, that's precisely GB1 is the x component of the boundary force, so I can just put them equal 0, and I could have just defaulted them to begin with, and I don't need to put it in the other. So basically the boundary conditions are extremely easy, and now we just need to get some graphical output. Let's do a 20 by 20 output grid, and this is just if you want to zoom in on part of the area. Okay, the only plot I want to do is a vector plot of u comma v, so that's 4. And the two components of the vector to be plotted are u and v, so that means 1 and 4. Do I want to undistort? Yeah, I don't want the arch to look distorted. And, well, those are, okay, u comma v is what I'm plotting. Now you can also do a stress field plot. Let's not do that. I'll show you the one in the book, but it's pretty easy to do. It automatically does a stress field plot, but we're essentially done here. And let's try running it. And the integral is of v is minus 737, which is correct value, so everything's working. Now let's look at the plots. There's the initial triangulation. Remember, we made a grid in the r and theta, p and q, a p and q grid, r and theta grid, and in each grid square there's automatically generated 4 initial triangles. So this is initial triangulation, but it was all generated automatically. And then the final triangulation, there's the final triangulation. We said we wanted 1,000 triangles, so the 400 were divided. And there's the displacement field, where the displacements are 0 here and here. And the only force acting on this was the body force, the gravity of the arch itself. And it's so that it sags most in the middle, which seems reasonable. Okay, now we're going to do a 3D example, and we have to use a collocation method with PD2D. So it has to be a simple region, and this is kind of like the each cross section here is like the arch we just did, but it's a three-dimensional. It's a thick airport hangar or something. And can we express this in terms of parameters with constant limits? Yes. We're going to let x just be p1, and so p1 will go from 0 to 10. And then y and z will be expressed in polar coordinates, with r going from 6 to 10 again, and theta going from 0 to pi. So here are going to be the parametric equations, where p1 is just x, it'll go from 0 to 10. And p2 is going to go from 6 to 10, that's r. Theta, y and z are expressed in polar coordinates, x is still x. And theta is going from 0 to pi, because it's half of a circle. And there'll be an external boundary force again, namely 0, 0, minus 10, only in the, due to the weight of the arch itself. And again, we're going to take E to be 100 and Poisson ratio to be 0.2. And we're going to have 0 displacements on the bottom where the arch touches the ground again, but also at the front. So we'll have zero displacements at the bottom here and the bottom there. That's where P3 is 0 in pi. And the front here where X or P1 is 0, but not on the back. So the other three, so they're, with a 3D problem with PD2D, you're going to basically have 6 boundaries. P1 equals its 2 extremes, and P2 equals its 2 extremes, and so forth. So we've got at most 6 boundaries. 3 of them are going to have 0 displacements, U and V and W equals 0. So it's basically glued to the ground and nothing can move here and here. It's also glued to some wall. There's a wall back here and it's glued to. But on the top and the bottom and the far side, we're going to have 0 forces. Okay, so this is a full 3D problem here. Steady state, so we're going to take the left-hand sides to be 0. It's quit changing with time. And the stresses are defined in terms of the displacement derivatives as follows. But for the collocation method, we have to actually differentiate all that. In other words, we have sigma xx, the derivative of sigma xx with respect to x, so we're going to have to differentiate that with respect to x, plus sigma xy with respect to y, plus sigma xz with respect to z, and we're going to have to actually differentiate those. Well, the e and the nu are constants, so it'll just be second derivatives on u, v, and w. And it's kind of a mess, but I've written it out for you here. So these will be the 3 partial differential equations. This is the derivative of sigma xx with respect to x. This is the derivative of sigma xy with respect to y, derivative of sigma xz with respect to z, and so forth. And the F is 0, 0, minus 10. So these 3 are all set to 0, and there are your partial differential equations. They're second order, more complicated than Galerkin. And here A, B, and C are defined as follows. I didn't want to put all this in terms of E and nu, too many constants, so I defined A, B, and C in terms of E and nu and use those there. But anyway, so I'll have to define these as constants, and then those will be your 3 partial differential equations. Now the boundary conditions on the fixed boundary would just have u, v, and w equals 0, which is easy, but the other 3 boundary portions, the bottom and top and the far x equals 10 side, remember the boundary conditions are when the boundary force G1, G2, G3 is given, then these are the boundary conditions. And for the Galerkin method, the left-hand side is just the natural boundary conditions. So all we had to do is set GB1, GB2, and GB3 equal to those. For collocation, we've actually got to write all that out because it's not so natural. And that's going to involve first derivatives, not second derivatives, because there's no derivatives of the sigmas here. The sigmas are functions of the first derivatives of u, v, and w. So in the 3 boundary segments where the forces are given and are 0, we're just going to have this. This is just sigma xx times nx plus sigma xy times ny plus sigma xz times nz. And we'll just have to write all that out. Will have already defined A, B, and C. But, well, that's going to be a mess to input on 3 different boundaries, so I'm going to do that. I'm going to cheat again and read it from a file just to save some time. Okay, here we go. Well, here, I'll let you have a peek at my pd2d.n file that I prepared ahead of time. That's where I'm going to define A, B, and C in terms of E and nu, and the 3 partial differential equations, and then the boundary conditions. I'll have to input that 3 different times. So I'm going to be reading from this just to save time. And so don't want to do a prepared example. 3-dimensional problem. It won't ask you whether you want Galerkin or collocation. You don't have any choice. It has to be collocation. Double precision. Okay, parameters. E is going to be 100 again. Nu, which I define as V and U is 0.2. And now I want to define A, B, and C, but I'm going to read that from the file. So A is defined as E times 1 minus nu over 1 plus nu, etc. B is defined here. C is defined there. I could have normally would have to input those by hand, but don't want to waste your time or my time. Okay, I guess that's all the parameters we need. Now we define the parametric equations, and the x is going to be just P1, y is going to be P2 times cosine of P3. Z is going to be P2 times sine of P3, so basically P1 is x, y is r in the yz direction, and P2 is r and P3 is theta. And how many grid points do I want in the x direction? Let's say 12. And x goes from 0 to, P1 goes from 0 to 10. P2, that's the R, that's going to go from 6 to 10, and let's put about 8 grid lines in that, from 6 to 10. Again, you can make these non-uniform grids easily enough, but I'm satisfied with uniform grids now. And theta goes from 0 to pi. Let's put in 12 theta values. Recommended solver is 1 for the collocation method. It's steady state. Linear, yes. Now I have 3 equations. And the unknowns, I'm going to call them U, V, and W. Do I want an integral? Yes, only again to check my work here. I want to integrate the absolute value of U plus absolute value of V plus absolute value of W, just so I can compare it to the, whoops, no, I need to put it, this is asking for the number of integrals I want, and now that's asking for the integral that I want. And I don't want any boundary integrals. Okay, now I need to define the partial differential equations, and I'm going to read those from the file. So input a pound sign, and it will read, let's go back up, well, can't hardly see this here, but here F1, F2, and F3. You can see F2 and F3 normally would have to input those by hand. They're in terms of second derivatives of U, V, and W, and the constants A, B, and C. And there's your minus 10. F1 is 0, F2 is 0, F3 is minus 10. Don't have any periodic boundary conditions this time. Now the 6 boundary conditions. Okay, P1 equals 0, that's the front end, and we glued that to the wall, so U, V, and W are going to be 0. So I put in U, V, and W is what's going to have to be 0 and 0. Now on the back wall, I have no boundary forces. That's the complicated equations, but I'm going to read those from the file again. There they are. It's exactly the same as if I topped all that in, but I don't want to do it. Now this is the P2, that's R, equals 6. That's the under thing. That's a free boundary, also 0. So I put those in the same way. And the top, same thing. Now P3 equals 0. That's the right. That's where it touches the boundary. So U, V, and W need to be 0. That's where it touches the floor. And P3 equals pi. Also U, V, and W equals 0. That's where it, the other leg of the arch. These are just variables that you need to define if you want to output something non-standard. Okay, the output grid, this has nothing to do with accuracy, just with the output. And let's see, what am I going to use here? And I don't want to zoom in, I want to see the whole thing. Now, For 3D problem, the graphics are a challenge because it's hard to display the solution, especially the solution here is a vector. So we're trying to represent a vector, three-dimensional vector in 3 space. So that's kind of hard. But PD2D allows you to do some cross-sectional vector field plots. So that's what we're going to do. I put in 1 because I want x equals constant, P1 is x constant, and I want to do 2 cross sections at x equal 5 and x equal 10. I won't bother at x equals 0 because I know u, v, and w are all 0 at the front end to the back end. I don't know. Now, again, this is challenging to get plot a vector, but we're going to do cross sections at x equals 5 and 10, so that's P1 equals constant. But I want to do P2 and P3 are really r and theta, so I want to choose I plot equals to 1, which will mean that instead of cross-sectional plots of P2 versus P3, it'll do plots of P2 cosine P3 and P2 sine of P3, which is what I really want. In other words, y and z. And now it does in-plane vector and an out-of-plane vector. It does an in-plane vector with little arrows and an out-of-plane vector, which be the x component, as a contour plot. So my in-plane vector will be, I want to plot v and w. See, these are x equals constant cross sections, so the displacement in the y and z directions are what I'm really interested in. So I put 5 and 9, that will plot v and w, and then v3 is the out of plane one, and that'll be 1 u. I'll just plot, so plotting u as a contour plot and v and w with little arrows. I want undistorted region again. So I'm going to plot vector v comma w with a contour plot of v. And I'm done. Okay, well, let's run it. The integral of absolute value of u plus absolute value of v. Well, I got an error message that the memory was exhausted. That's because I'm running on an old computer with not very much memory here. So I decreased the grids to where it looks like it'll fit into memory, but it may take a good bit of computer time on this. Remember, we got 3 equations in 3D, so this is kind of an expensive problem. But so let me just pause it until it runs here. Okay, it ran with the less fine grid, and the integral is about correct, so it looks like it's working. Now let's look at the plots. Okay, here's the plot at the x equals 5 cross section. That's right, sliced right in the middle. And here it is at the far end, x equal to 10. And well, the VW field looks pretty much like the 2D and then there's a contour plot of u, which is a little hard to read. Well, in the book it shows those 2 plots that I just showed you, but with a little more better grid. They look pretty much like what I showed you, though. Now, problem 3 shows the stress strain, the elasticity equations in axisymmetric form. That means if you have a region where it's clear that the solution doesn't depend on theta, if it's in like a region that's symmetric around some, say, the z-axis, and then it's clear from the boundary conditions and everything that the solution is going to be independent of theta, then you can reduce it to a two-dimensional problem. It's much, much simpler. But it's kind of surprisingly what it looks like. It's not, maybe not what you expected here. So now in 2 dimensions, the variables are r and z. There's no theta. We're assuming that nothing depends on theta. So it's r and z. And that much looks pretty much like you'd expect. But there's some funny stuff in here. This is actually derived in the next problem. It's rather complicated. The derivation of the axisymmetric elasticity equations is really quite complicated, problem 4. But here's the results. And if you have a problem like problem 3 is an axisymmetric problem, basically your region is like a, well, if you take this, so this is r equals 0, this is the z-axis here. If you rotate this around the axis, you get basically a cylinder with a notch all the way around. So just imagine rotating this all around. Then nothing's going to depend on theta, so you can solve the problem as a two-dimensional problem, and that's what's done here. And let's see, there's some forces at the top, and that's causing large stresses at the notch. But anyway, axisymmetry can sometimes be used, if you have axisymmetry, to reduce down to a two-dimensional problem, and if in that case it's much, much simpler. In fact, you can even use the Galerkin method for it now, which is what's done.